Welcome to the course MCDM techniques using R. So, today we are going to talk about one important aspect of MCDM techniques, that is sensitivity analysis. So, we have in this particular course we have covered a number of techniques starting from AHP and we up to fuzzy AHP. We talked about Elector, we talked about Topsys, Vicar. So, all these techniques and the kind of steps, the kind of method that are followed there is always a chance that if we change the input input variables values, if we change the input values, then that is going to have an impact on the final results, the ranking that we typically produce. So, how do we analyze whether a particular model is providing robust results or not, whether slight changes in the input values whether the model results are going to be robust with respect to that, whether the model results are not going to be changed just because of slight variation in the input values. So, all that discussion comes under the this topic, that is sensitivity analysis. So, let us start our discussion on the same. So, how do we define sensitivity analysis? So, one definition which is here, that study of how the uncertainty in the output of a model, whether numerical or otherwise, can be apportioned to different sources of uncertainty in the model input. So, this uncertainty in the output of a particular model that we are talking about is with respect to the uncertainty that is coming from, that is originating from model input. So, with respect to the model input variables, the model input values, the changes and the uncertainty that can come from there, how the model results, how the output is actually impacted. So, that comes under the domain of sensitivity analysis. So, as you can see, main idea being so there are many advantages of sensitivity analysis, many things can be done. Few aspects of sensitivity analysis we have covered in some of the starting lectures. However, the main benefit or main idea being testing the robustness of the results of a model or system in the presence of uncertainty. So, how robust the results of a model are. So, how do we check that? So, that comes under the domain of sensitivity analysis. So, as you can see in the third point also that input data is slightly varied to observe the impact on the results. So, this is what we tend to do in a sensitivity analysis. Now, there are a number of approaches that are available to perform sensitivity analysis. So, we are going to talk about most popular one or rather commonly used one. This is one at a time approach or OAT or OFAT approach. So, here what we actually do in this approach is that we first step is moving one input variable, keeping others at the baseline or nominal values, or we can also say that keeping others constant. So, we move one variable, we vary one variable and keep other constant, and then we can bring back that variable to its nominal value and then repeat the same exercise for each of the other input variables. So, this is what we do. We pick one parameter, one particular variable that we would like to change, and we would like to analyze the impact of doing certain changes, doing slight changes in a particular input variable on the output of the model, right. And then we bring this variable back to its normal value, right, nominal value and the baseline value, and then we try the same thing with the other input variables. So, in that fashion for each of those input variables we can always find out, we can always analyze how the model output is sensitive to changes in those input variables. So, sensitivity of the model output with respect to the changes that we do in the input variables, that can be analyzed. So, let us move forward. So, few criticism of this approach are also have been done. So, one of the important criticism is that does not take into account the simultaneous variation of input variables. So, a particular model might be based on a number of input variables. However, the approach that we are talking about, one at a time approach, the more commonly used approach, it does not take all the variables in one go and then test the test the sensitivity of the model with respect to the changes in those all of those input variables. Rather, it takes the variables, so the input variables one by one, and then we analyze the impact on the model output. So, therefore, what will happen is we cannot detect the presence of interaction. So, if some of the input variables are having certain interaction, that cannot be detected through this approach, because we are taking one variable at a time. Now, through under this approach we typically use scatter plots to actually analyze the results of sensitivity analysis. So, once we have done our sensitivity analysis modeling, then we can use scatter plots to analyze the results, because the as I talked about, the sensitivity analysis is about analyzing the output of model with respect to changes in the input variables. So, output variables against individual input variables, which are of course after randomly sampling the model over its input distribution. So, after obtaining that, we create these scatter plots, and what we get in this scatter plot is a direct visual indication of sensitivity. So, when the input particular variable, when a particular input variable is varied, then how the model results are actually changing. So, we get a visual indication of the sensitivity of the model. So, now what we are going to do is that we are going to apply this approach. We are going to do an exercise in our studio, in our environment. So, the example that we are taking here is a choice of a sport shop. So, we have 4 criteria for this particular decision problem. So, these criteria are visibility, frequency, competition, and renting cost. So, if someone is looking to decide where they should open their sports shop, then these could be important criteria, because this is like a identification of geographical location where you would like to open your shop. So, alternatives are 3 alternatives are there: city center, shopping center, and industrial area. So, all these alternatives, they have their own pluses and minuses. So, which are and these alternatives are to be analyzed, are to be compared with respect to the criteria 4 criteria that we have: visibility, visibility of the shop, how many customers are going to able to visually locate the shop, frequency, number of targeted customers visiting around that area, competition, whether there are any other sports shop in the nearby in that same region. So, renting cost, what is the renting cost if you want to open a shop, how much rent you will have to pay for that that locality. So, depending on these 4 criteria, we are going to decide on which is going to be which is the best alternative among these 3: city center, shopping center, industrial area. Now, city center is mainly this is more of a prime location, higher renting cost typically at the center of the city. So, possibility of targeted customer and then the frequency of targeted customer being coming to the city center is higher in comparison to the other areas. If we look at the shopping center, it has its own characteristic, slightly medium level of renting cost, competition also a medium level, and so this is like a medium level location. Then the industrial area is there. So, the industrial area typically might be outside the city, in the suburban areas of the cities. Rental cost might be on the lower side, competition might be on the lower side, but frequency and visibility. So, this is in that sense these three alternatives are going to have their own characteristics. But here it is important how do we quantify whatever these criteria are with respect to them, how we are going to quantify these things. So, as we have discussed in our AHP, we have covered AHP and fuzzy AHP in this particular course. So, we are going to use the AHP, the traditional AHP for this sensitivity analysis. So, let us open RStudio. So, the package that we are going to use for this sensitivity analysis is fuzzy AHP package, something that we have used in the previous lecture. So, this package, why we are selecting this package, because the other two packages that we have covered for AHP method, the way the model function is defined, we cannot actually change the criteria weights. If we change the criteria weights, that is not actually directly being taken as a input argument by those model functions. However, the model function that is available in fuzzy AHP package, that takes criteria weights as an input variable. So, therefore, any changes that we do in the input variable for the criteria weights, that can actually be the impact of those changes can be very easily analyzed. So, for this reason, because of the suitability of the model function that is there in fuzzy AHP package, we have selected this particular package for our sensitivity analysis. Then we are using another package PSE. So, this gives us the functionality that is required for us to perform sensitivity analysis given a model function. So, this particular package imposes its own restriction on how the model function should be in terms of how it is going to receive the input variables values, and so in terms of that there are certain restrictions. And so, the package the function model function that we have in fuzzy AHP, we will have to do certain coding, we will have to write wrapper for the model function, so that we can use the function existing functionality in the PSE package and perform our sensitivity analysis. So, as we talked about the decision problem, goal is choice of a sports shop. We have 4 criteria: visibility, frequency, competition and renting cost. We have 3 alternatives: city center, shopping center and industrial area. So, let us start our exercise. So, first we have pairwise comparisons of criteria. So, here we have 4 criteria. So, the matrix that we are going to require for pairwise comparison is 4 by 4. So, certain values, as you can see, are there in the first line of code here, and these values are going to be used for the are being used as pairwise comparisons of criteria. So, let us so the same function that we have been using in previous lectures as well, matrix function, to to generate the comparison matrix for criteria. So, we are using, so first argument is using the combined function C. So, all the values that we require, all 16 values that we require have been combined using this function, and then number of rows, number of columns 4 and 4. So, let us run this code, and you can see in the environment section we have generated criteria PC. This matrix is there. Now, we are going to give appropriate names for this matrix, row names, the names of criteria, then column names, name of the criteria, and this is how our as you can see in the console output, this is how our criteria matrix comparison matrix is going to look like. So, you can see here. Now, what we are going to use is we will have to, because the fuzzy package that we are using that we are going to use is actually having its own class of objects, and therefore, though we have the comparison matrix, we need to convert this comparison matrix into a format that can be understood by fuzzy AHP package function. So, therefore, what we are going to do now is we will load this library fuzzy AHP into our environment. So, this is loaded, Now we are going to use this pairwise comparison matrix function available in this package, as we did in the previous lecture. So this is going to create us a comparison matrix for criteria, which can be used for other functions in this particular fuzzy AHP package. So let us run this code. Let us print the this matrix. So you can see, just like in the previous lecture where we use the fuzzy AHP package, you can see this is an object of class pairwise comparison matrix, and you can see their values in the character format are displayed here in the first slot. The second slot, values in the numeric formats are displayed here. As you can see, the same thing we did in the previous lecture, and the variable names are also given here in the last slot. So this is a slightly different package requirements and the class of objects that are being used. So they have created their own class of objects. So therefore we need to use their functions to change to convert our variables in the appropriate format. Now what we are going to do is we will compute criteria weights. So again we are going to use this calculate weights function that is available in this package. So the matrix that we have just computed, so that is going to be passed on as the argument, and we will get the weights for criteria. So let us run this code and print the weights. So you can see criteria weights for visibility, it comes out to be 0.5845, frequency 0.1037, and then competition 0.1187, and then the renting cost 0.1931. So so now we have computed the criteria weights. Now let us move forward to pairwise comparisons of alternatives with respect to criterion visibility. Similarly we will do for other criterion. So here again you can see we are using matrix function and the combined function C function, so that we can initialize these scores, pairwise comparison scores for alternatives with respect to criterion visibility. So let us run this code and we will get a matrix. Let us name the these row names and column names of this matrix, and our matrix is going to look like this. You can see here city center, shopping center, and industrial area, row name and column names, and you can see the values. Now we are going to convert for this comparison matrix for alternatives also, we are going to convert into a class of object which can be used by the functions of fuzzy AHP package. So therefore again we are going to use the pairwise comparison matrix here and calculate weights here. So we are going to compute scores for alternatives with respect to criterion visibility now in the format which is suitable for fuzzy AHP package. So let us run this code. Let us compute scores. Let us print. So now we have got this scores with respect to visibility visibility criteria. So each alternatives and their scores. Now now what we are going to do is the similar kind of exercise we are going to perform for for other criteria. So the frequency is the next one. So again matrix and the combined function to create the pairwise comparison matrix, then row names, column names. This is our comparison matrix as you can see in the console output. Now again we are going to compute scores using these functions, pairwise comparison matrix, and then the calculate weights. Now you can see these scores for these three alternatives with respect to criterion frequency. So this is done. Now let us move towards the next computation, that is pairwise comparisons for alternatives with respect to our next criterion, that is competition. So again let us run this, row names, column names, and these are the values. Now we are going to calculate scores. So again first we need to use this function pairwise comparison matrix, so that it is in the suitable format, and then weights. let us see the weights. So, these are the weights. So, these are the scores for alternative with respect to criterion competition. Now, the last criterion, that is renting cost here. So, now again same set of similar set of lines here again for renting cost, row names, column names, the matrix, and then pairwise comparison matrix function, then calculate weights, we will get the scores and then the scores for. So, these scores for alternatives with respect to renting cost criterion. Now, once we have got these scores, we can create our decision matrix. So, as you know, in the decision matrix what we require is on the column side we will have the criteria, on the row side we will have the alternatives, and the performance of these alternatives with respect to with respect to each criterion is to be there in the decision matrix. So, what we are doing now is we are going to extract these scores that we have just computed. So, first visibility with respect to visibility criterion, then frequency, then competition, and then the renting cost. Here, because the way these classes are defined, you see we are using these scores alt visibility weights which we have already computed at the rate of weights to actually access the weights in their numeric format. So, this is the notation that we need to use, so that we are able to access the values, because right now we are interested in the values here. So, we are trying to extract that value in this using this particular piece of code. Now, we are using a name function also. So, right now we are interested in the values and not in the names that have been given there. So, we are unnaming the row names, column names that we have been assigning. So, we do not need that, and some of those names have been assigned by the functions of the fuzzy ASP package as well. So, we are going to remove the those things and just extract the values here. So, column 1, column 2, column 3, column 4 these are with respect to 4 criteria that we have. So, let us extract these scores for alternatives. So, first column 1, column 2, column 3, column 4. Now, once we have these 4 columns of scores for alternatives, we are going to combine these 4 columns to generate our decision matrix. So, for this we are going to use cbind function. So, cbind function is actually for columns to bind a number of columns. So, these column 1, column 2, column 3, column 4 we already have already computed. Now, we are going to use this cbind function to create our decision matrix. So, let us run this. Now, again we are going to name the columns and rows. So, again columns criteria criteria names, and rows alternatives names. So, you can see now we have the decision matrix in the console output here. So, you can see in the column side these are actually criteria names, and on the row side what we have is alternatives. So, performance of these alternatives with respect to each criterion, and you can see the scores there in this matrix. Now, we have the computed criteria weights also, and we have the decision matrix also. So, therefore, we can go ahead and use the function, the model function, that is calculate AHP. So, in the calculate AHP, first argument is the criteria weights, second argument is the values, which is decision matrix. So, when I was saying at the start of this lecture while discussing sensitivity analysis, that why we have picked up selected this particular package, because the model function calculate AHP, this is actually taking criteria weights as the input argument, which is something that is not available in the other packages. So, therefore, it is easy for us to slightly vary these weights, input values with respect to input values with respect to criteria weights, and we can analyze the impact on the model output. So, therefore, now what we are going to do is we are going to do a simple run of AHP modeling. So, let us run this code. This is to tell you that given the pairwise comparisons that we have initialized and the weights for criteria that we have computed and the decision matrix that we have computed. This is our model result. So, as per this result, the city center is ranked 1, and then followed by shopping center, and followed by industrial area. So, you can see the values for shopping center and industrial area are very close, and value for score for city center is actually on the higher side. So, city center right now, given the model results that we have, city center is the best alternative. So, you see when we were discussing this particular decision problem, we said that probably city center is also going to be more expensive because of the prime location of the city and all that, but despite that, as per the model results and as per the input data that was provided, city center comes out to be the best ranked alternative there. Right now, so now what we are going to do is we are going to perform our sensitivity analysis, and because we are using that one at a time approach. So, in that approach we are going to pick the renting cost criterion as our input parameter. So, keeping all other values constant, we are going to change the weight for this criterion renting cost, and will analyze the impact on the model output. So, our selected parameter is criterion renting cost. So, you can see a few comments there also, that how ranking will change with respect to changes in renting cost weight while keeping all other values constant. So, this is something that we are looking to perform. Now, first thing that we need to declare here is the parameter names. So, which I have already mentioned, that is renting cost. However, the function in the PSE package that we are going to use is there is some problem in the function, in the sense it is not it produces a number of errors if we are using just one parameter. So, this function is actually designed for simultaneous changes in a number of parameters and analyzing the impact on the model output. And when we use just one parameters, you might encounter certain errors there. So, to camouflage, to overcome this situation, because we are using one at a time approach and we are going to use just one variable, going to change this one variable, and looking at the impact on the model output. So, given the approach that we want to implement, we are using a dummy parameter to camouflage, to overcome the functionality that we have noticed in our experience for this package, PSE package and LHS function in particular. So, LHS function is actually to generate the hypercube there. So, depending on the requirement, depending on the argument that we need to pass on to this function, we are going to create certain variables and initialize them. So, first one is factors, this is to name the parameters. So, we have two we have just one parameter renting cost, the other one is dummy, which is just to camouflage the function. So, let us run this. Then probability density function and the required arguments for those function. So, here we are using uniform distribution. So, we have the quantile built in function available in our environment. So, we are using QUnif for our parameter. So, let us initialize this variable also, so that we can select our probability density function. And then the certain parameters that are to be used by these probability density function QUnif. So, that is mean value and max value. So, that we have passed on as 0 and 1, because the criteria weights, it has to be between 0 and 1. So, that is the range where the values should lie. So, that is something that we have initialized. So, let us run this code. Now, we are also recording the current value as per the model result that we have in this variable current renting cost. So, given the model results that we had, we are just recording this. Later on, we will be using this value. So, let us record this. Now, I have written a wrapper function. So, this wrapper function is actually designed to receive a data frame that contains all parameter combinations. So, right now we have two parameter combination, one is renting cost, the second one is the dummy. So, all the data frame should be containing all these parameter combinations. However, if we look at the model function, our model function takes just one set of these combinations and produces the model results. So, therefore, model function cannot be used directly. Therefore, we need to write a wrapper function which keeps on taking the values one combination each at a time and keeps on generating the model results, because later on we will be using these number of runs of model results and produce output to analyze the sensitivity. So, this one run function is there. So, what it does is we are taking this value of renting cost, which is going to be varied using the uniform distribution as we have detailed earlier. Uniform distribution between 0 to 1, the values are going to be produced as per the quantile function QUnif, and these values are going to be passed on to this wrapper function and will get a number of model output. So, how this function is going to behave is first as you know that calculate AHP here, it is going to take two arguments, one for criteria weights, another for values. So, values we are not changing, because as I said one at a time approach. So, we are not changing other things there. So, values not supposed to change, and the other criteria weights that are also we are not supposed to change. So, here you can see that we are just changing one value that is associated with the renting cost in this line of code. So, that is changed, and then the weights are passed on to calculate AHP function and we will get the model result. Now, let us run this code so that this function is defined. Now, we have model run function which is actually calling this one run function by passing on these each time one set of combination. So, this is the function that is actually the wrapper, and it is just calling one function. So, here we are using mapply, and one run is being called upon using the values of second and third arguments, parameter 1 with respect to renting cost, parameter 2 with respect to dummy, that is that will not do anything. As you can see in the one run code, we have not used live dummy anywhere, it is just being used as as a dummy, as a camouflage there. So, will model run. So, every set of combination, this one run will be called and the model result output will be produced. So, let us run this code and we will get the result. I will define the function. Now, these functions are defined. Now, we are going to use this we are going to generate hypercube for the model. Size of the hypercube is 1000, that means we are planning to generate 1000 samples. So, actually 1000 model results are going to be produced, and we will be analyzing the changes with respect to these 1000 points, 1000 sample points. So, when we said model function, this is now accepting data frame, and 1000 set of combinations of arguments for one run is going to be produced and passed on using the LHS function, and then the one run will execute and produce the results which are going to be recorded. So, let us load this library PSE, so that we need, so that so this package is right now not installed. So, let me first install this package so that we are able to use the function. So, as we have been doing in other lectures, we have to type install.packages, and within the double quotes we have to type PSE, and this package will be installed. And then we will be using the LHS function that is available in this package. So, first argument, as you can see in the code, is the model run. So, in this package LHS we are going to call this model function, which is actually a wrapper for the original model function calculate AHP. So, this is going to be called, and the input parameter that we have renting cost. So, this input parameter is going to be varied and the output would be recorded and will generate the hypercube. So, package is now installed. So, let us load the library into our environment. So, once this is done, we will be able to use this function. So, this is done. So, now let us talk about this LHS function. So, model run, which we have just defined, factors are the names of the parameters already defined. 1000, that is the number of sample points that we want to generate, the size of the hypercube. Q and q dot arg we have already defined, and results names, that is we have 3 alternatives. So, as you have seen in the calculate AHP model results, we got 3 scores for these 3 alternatives, and city center was the best alternative. So, we are just giving out these names so that it could be used by the function. So, let us run this code, and because there are 1000 sample points, this takes a bit of time. Now, we are going to record the output of this LHS function, the results, the model results that have been generated. So, we are going to record them here in this data frame. So, as dot data dot frame is the function, and we will record this. Then renting cost, these values data that has been generated by this function to run the model, that also we are recording here, the parameter renting cost. So, this is also available, you can see in the environment section as well, that here p renting cost is there, p renting cost, and the data frame that we have just created, that is also the df is there, 1000 observation, 3 variables, because with respect to 3 alternatives that we have. Now, once we have generated in the output, generated the hypercube. Now, what we are going to do is we are going to plot. So, we are going to plot this correlation between parameter, that is renting cost, and the model result, right. So, these scores that we have for alternatives, so they are going to be plotted with respect to the parameter. So, let us look at the range of these variables, so that we can use that in our plot function. So, let us look at the range. So, this range is, so all these ranges are anyway going to be between 0 and 1. However, for certain other variables, in other situations it could be something different. So, as a good practice, we can always check at the range. So, all these ranges as we can see 0 and 1. So, this also gives us confirmation that everything is going fine in terms of being within the range. Now, we are going to use a plot function where first argument is the parameter p renting cost. This is going to be plotted along the x axis. Then we have df1, which is with respect to city center. So, this is going to be plotted in red color, and then we have lines function, grid function, which will just create the grid, and lines function, which will plot the on the y axis the second output, that is with respect to shopping center. Then the third one, lines function, this will plot the output with respect to industrial area. So, let us run some of these code. So, plot, you can see a plot has been generated here. Now, let us run the, so grid does nothing but it creates a certain line, so that to give us a sense of where the values are lying there. So, let us run another line of code. So, lines, this is now, so first one was city center, then we have shopping center. Now, let us plot the industrial areas, this is also there. Now, the current value of renting cost, the model output that we had, right. So, the model output with respect to the current renting cost value that we have, will also plot that as a vertical line here, you can see this is around 0.19. So, and the model output as we saw was city center was the best alternative, as I described there. It had value around 0.41, right, and the other values for the shopping center and industrial area were around the range of 0.28, 0.29. So, you can see here in the graphic, so that being the case. So, let us run this legend also, and now we can analyze this graphic. Now, let us analyze through this plot. So, on the y axis we have alternatives, we have 3 alternatives: city center, industrial area, and shopping center. So, you can see in the legend that is mentioned. So, red one is the city center, the green one is the shopping center, and the blue one is the industrial area, and the black line that you are seeing around the point 19, that is the current model results. So, if you look at the current model results, city center came out as the best. The same thing is similarly it is depicted here as well. Now, if you look at here, if you look at the model, we change the value of renting cost from 0.19 to something about 0.4 or more than 0.4, then you would see that industrial area would become the best alternative. So, therefore, a big change in the renting cost would be required to change this alternative. However, once the weight of renting cost goes more than 0.4, about this point here, more than this, then the industrial the industrial area is going to remain the best alternative, right. So, from looking at this graph, we can clearly observe that shopping center, it is it is never going to be the best alternative. So, till about 0.4 value of renting cost, it is the city center, and after that it is the industrial area. Similarly, we can analyze the sensitivity of results, model results, with respect to other input parameters, other criteria that we have, and we can find out which is the critical criteria. The model results are sensitive to which criteria in a relative sense. So, all that can be analyzed through these kind of graphics that we have just computed. So, with this we conclude our discussion on sensitivity analysis, and this is also the final lecture of this course, MCDM techniques using R. So, we have been able to cover a number of techniques starting from AHP, Elector, Topsys, Vickers, and fuzzy AHP, fuzzy sets, and we have also talked about in today's lecture on sensitivity analysis. So, we have been able to cover a healthy portion of MCDM techniques, and based on the responses that we receive from your side on the NPTEL platform, we will definitely plan for another part of this course, where we would be covering another set of MCDM techniques, and you will also get a flavor of R environment, how to do modeling, how to write your code and check results, do your analyses in R environment also. So, hope you enjoyed the course. Thank you.